So before we turn to back to circles and whatever we can do with them using vector algebra, first let's take care of the unfinished business from yesterday, and that is the incremental way of writing or modeling accelerated motion. Okay, so this is the formula is already here, but just the way we did last time was explicit. So we used the top formula, which is closed form formula, and the next one is in fact the incremental formula, approximation for motion, which is uniformly accelerated. In other words, the acceleration is fixed. Okay. So we're going to just do it from scratch. This is, once again, what we did last time. That is explicit direct formula. Let's start over with, and do it the right way. Okay, so I'm going to remove all of this. And I'm going to be doing actual motion more than so not any kind of multidimensional space, just motion on the plane. Okay, so I'll just erase everything and we'll do everything from scratch. So that is in many ways what you're going to be doing in many of your projects. This is how it starts. So there's a physics setup. Which is, what is it, just acceleration, acceleration, initial position, initial velocity, and then you can model the whole thing here, which is what we're going to be doing. So, okay, so we have interval, time interval, delta t, time is right here. I will be combining things, rather than doing one dimension at a time, I will be combining things into vectors. And so, say, this will be my acceleration. This will be my acceleration. Okay, so which is say x double prime. Okay, so 2 dimensions will be x prime and y prime. Okay, so that, I'm sorry, double prime. Okay, so I'll put them here. Okay, so let's just go ahead and start doing things. What are these? So we're talking about a ball thrown in the air. Okay. So what is the x double prime, y double prime? Acceleration?
This is 0 and y is gravity.
0 and what double prime?
Gravity, so 9.1.
Yeah, okay. First of all, negative, if we choose the vertical up. Then negative and is it 32 in feet per second squared? I think it is 32 feet per second squared. So that's what I'm going to be doing. And then for the time being, at least, we're going to assume that it is a constant acceleration. So just write it out. So this is a vector. This is a vector. So the vector takes 2 columns. If you do a 3-dimensional motion, you'll have 3 columns at a time. Okay. And now we're moving on to velocity. Okay. The next 2 columns here, velocity is x prime, x being the location actually. So and I'll have here x prime and y prime. Okay. So how do we do it? We start with the initial velocity. Okay. So this is t time equals 0. So in this column I will put numbers that are fixed. So it is our choice to throw a ball at the velocity that we want. So well, let's pick anything. So how do we want to throw it? Forward, up, forward. Anything? Give me a number, 2 numbers. Okay, suppose we throw straight forward. What are the numbers?
0, 1 and 0.
The second one is 0. Give me some reasonable number if you know from a baseball or whatever. What is the velocity of the ball thrown? Or you know, hit.
100.
100 feet per second. Yeah, okay, that's fine. 100 feet per second makes sense. Makes sense. So that is the initial velocity. Now, how do we compute the velocity then at the next moment, and it is actually quite transparent. Okay, so what is the horizontal velocity will be from this point of view at the next moment of time, after 0.1 seconds. That we did yesterday.
Wouldn't it be the same if our acceleration is
It will be the same, right. Right. So, but since I don't want to do it, I don't want to just write it is equal to 100. I want to have as general situation as possible. So the next time, once we finish with this, we'll play with this and change acceleration in a different manner. So it might be variable. Okay, so I want to do it the right way, and that means that I'm gonna write it in the recursive formulas, which will be the velocity now will be the same as the velocity 1.1 second before plus what? Something related to the acceleration.
Isn't it just
Yeah. The respective acceleration, this one,
right?
multiplied by
Be 0.1 because it's 0.1
yes, 0.1,
seconds.
the time, the period of time. That's right. So which is R2, R3C1, R3C1. Okay. Okay. So once again, the previous velocity plus the acceleration times time. This is works out is especially if I now put it for the y-axis. I'm not sure what. Hold on a second. What happened? I lost it. I didn't write it. I lost it. That's my formula. Spreading it to the right. Okay, so you see what has happened with y prime. The same formula. Let's take a look at the formula. What it gives us. As you can see, it's the same formula. Previous y velocity is equal to plus the acceleration times the time interval gives me the current velocity. Okay, and as you can see from 0, it starts to go. It becomes negative. Okay, actually. So the acceleration goes down. It pulls it down. So this is if I spread it down. That's what I'm going to have. Okay, so as you can see, the acceleration is visible. Okay, so that gives us only the velocity, and now, certainly now, the last step is the location, so that is my location, say, x. And I have x here, y there. Okay, once again, we need initial velocity, so suppose it's a person throwing at a position is, well, let's place it at 0, but the height, say, 6 feet. Okay, makes sense? And but the rest is the same. Now, what are the formulas that I apply to the position? Remember, the relation between the velocity, between position and velocity is the same as between velocity and acceleration. So velocity changes position, acceleration that changes velocity. So if we know how to compute the velocity from the acceleration, the exact same way we compute the position from the velocity. Okay, so once again, if I have a reference here at the velocity to acceleration, now I do the same. I simply copy this over here. Okay, and then the reference. Let me show you. I take these and I copy them over here. Then look at what this means. I'm referring to my y position will be my previous position 6 feet, and at 32, and in reference to the current velocity, or vertical velocity. So my vertical velocity multiplied by time is by how much I have moved in that direction. Okay. In the meantime, you notice what has happened with the horizontal velocity. It would progress by 10. Why? Because the horizontal velocity is 100 multiplied by 0.1, and naturally every time that velocity is not changing. Okay, and every time it will progress by 10. Okay, so don't be surprised that it's not entirely reasonable. What is in this model is missing. the most important part probably.
Friction?
No, I'd say, air resistance is kind of friction. So that would slow down the flight. But otherwise, well, yeah, so as you can see, what we do discover is without the air resistance, this is where numbers become negative, y become negative. What does it mean?
Passes the x-axis. Goes to-
Right, well, I mean, practically speaking.
It hits the
Goes
ground.
under
It hits the ground.
Yeah.
So it hits the ground, and then we probably should stop and start over. But I mean, if it's just happening too quickly, and you still want to analyze, you can, instead of 0.1, you can have 0.01, and it will give you more information, and it will just progress slower, as you can see, very really slowly. And then to understand what's going on, you will need more data. But what really we care about is, so here you can see when it, more precisely when it hits the ground, when it hits the, I didn't do this. Okay, so, well, our main interest is then, so it hits the ground after, here it is, so after 0.61 seconds. So if you throw 100 miles an hour forward, then it actually stays in flight half a second roughly, without air resistance. So our interest is really to visualize it. So we're going to visualize very simply like this. So I highlight the two columns, and then I go and insert the scatter plot. Well, this one, that's fine. Okay, so what's in the beginning happening is just some extra stuff that does not belong here. Okay, so as you can see, so it's made of dots. The formulas that it may have come from, it did come from, are invisible to Excel, so it plots points only. So you can see those. It's not really a line. It's this thick dots connected into a point. Into a curve. You can see it goes 60 feet ahead before it hits the ground. You also know that this is a parabola, and that's exactly where we reproduce what we learned theoretically from, I suppose, high school physics, that we supposed to have a parabola. We do. Okay, so the better at 0.01, I can improve accuracy if I wanted, if I just make the time interval smaller and smaller and smaller. Okay, so this is quite transparent. What we could do is we could certainly, for example, we could throw it up. Not entirely up, we could throw up forward. So say, let's make a little experiment so if suppose it's the same person, it still can throw 100 feet per second, but now he's looking to throw it as far as possible, and so the angle might change. So how do we do it?
Throw it at 40,
Speed is 100. What?
throw it at 45 degrees.
Right, so okay, 45 degrees, yes, we actually can confirm that 45 degrees is best one, but let's do it for any one. So S is equal to, I didn't do it right, S equal to 100, and here I'll put angle in, ideally, let's say 45 degrees, okay? But how do we actually compute the initial? It only affects the initial velocity. So how do we do it? Speed is 100, angle is whatever, 45 degrees or any other. So how do we compute it?
— 100 times sine of pi over 4?
Yeah. So let's just do that. So my initial horizontal velocity is cosine, in case you don't remember. So this is what it looks like. So this is 100, and then this will be 100 times cosine alpha, our angle, and this will be the vertical velocity will be 100 times sine alpha. Okay? so I put here this value, which is R1C. It's equal R1C 5 multiplied by cosine of my angle, which is R2C5. Okay? Well, except I have to do something about it, because I want to write angles in degrees, but I want to write I have to compute cosine with radians. So what do I put here?
Pi divided by 180.
Yes. Multiplied by pi divided by 180. Okay? So, okay, 70, that looks reasonable. And then I'll put it here to the right, except now I have to replace this sign with cosine with sine. Okay, so does it look reasonable? So I could let me do the I'm resizing it the chart so that we would have a more reasonable proportions. Okay, that's not actually. So we would recognize roughly at least that there is a 45 degrees furrow. So it's close, right? So it's reasonable, more or less, that we are throwing in 45 degrees. Let's vary. Let's confirm. So what is the how far does it go? Let me put here 0.1 again. So it lands. Okay, let me give it some more, maybe. Okay. No, wait a minute. Too much. What I meant is 0.5. Okay, so roughly you can see, so that's the throw at 45 degrees. It lands about 300 plus feet ahead. It appears to be, so the height is at the very end is very low. I could add a little bit of the data. So this is at the very end. This is where it hits the ground, right? This is y coordinate, which is very low, and then how far it went, 314,663. Okay. So that's how far it went, and we can confirm that by varying the angle, whether it goes faster or farther or not. So if I add, say, 50 degrees, so, well, we need more data because it's slower throw, but you can guess that it is roughly, it should be less. What happened? Catch all the data. Okay, so what I'm doing is simply recording making the chart to include all the data that was missing. So it just takes stays in the air longer. Okay, so that's what the picture looks like. If we throw at 45 degrees, you can, let me resize it so we can see where it hits the ground. As you can see, it is actually not that different, and we probably would have to look at the data more precisely to determine this is where it hits the ground roughly. As you can see, so the y number is 1.2, x number is 3.08 down from 314. Okay, so indeed it confirms more or less in a practical, more computational, experimental way that indeed 45 degrees is better than 50 degrees. Okay, if you change it more dramatically, this number from 50 to say 80, okay, so that number will noticeably go down to, as you can see, around 100. That's where it crosses the x-axis. Okay, so that's what you can do easily with the whole thing. You can change the angle. You can certainly change the throw harder. You can add third dimension, so you can throw in diagonally if you want to. And what else? The bigger thing, if you start modeling, say, something else, for example, maybe maybe more complex motion, maybe sliding on a slope, maybe strains attached or springs. Your acceleration first of all, it doesn't have to be look exactly like that. So, for example, hypothetically, what if we have wind? And suppose I could just add here, say 2. Why not? So how far will it go with the wind? I'm just adding 2 to the. Okay, so as you can see, well, you certainly can guess it goes faster, but all the formula is still applicable. And beyond that, you could actually have the gravity or any other force that's involved here. You can change it to become variable, because this computation works out just fine without it being constant. So I just put these 2 columns I can fill with any numbers that I want. So horizontal and vertical accelerations or horizontal vertical forces, and they might vary in any way you want. So okay, so we'll stop here. Just we have confirmed that it can be done incrementally with a spreadsheet. Don't forget that it is an approximation. After all, so up to this point, it's not an approximation. So acceleration is given, velocity is computed exactly. So as long as your acceleration is exactly constant, then your velocity will be exactly linear. So that part is not an approximation. But then for the next line, we assume that our velocity does not change within every time interval, and that's how we work it out. Okay. Small h gives you more accuracy, so that most of the time it works out just fine. Okay, so that's one of the simplest problems you can solve in this manner with nothing but a spreadsheet. So, but it does require, as you can see, understanding of little physics, relation between the position of velocity acceleration, initial position, initial velocity, and what amounts to different derivatives. So derivative of this is that. So these are vectors. Derivative of x is x prime. Derivative of x prime is x double prime, the acceleration. Okay. Okay, so we'll do more of that, but at this time let's continue on with what we started last time, and that is the circle. Let me circle it. Well, that's the simplest one. Written separately as 2 x and y unrelated, seemingly unrelated coordinates. This is better. That is our vector representation, or more like it's just the formula for the a vector formula for the parametric curve. So explicitly you can see how t is present, and then you compute sine and cosine. So it's also certainly not any trouble to do sine and cosine functions, plot the circle, which we then now can do as well. So if we look at what we did last time, so this was a parabola, but well, I guess I could insert easily the. Let me copy. Okay, so if I kill all of this, and if I just do I do the circle. Let me quickly plot the circle. It's not a big deal, but also I'll put x and y here. It's x and y, and I'll put here. Hold on, what is that column over here? Okay, I will put x and y here. Okay. So x is equal to cosine. Cosine, that's all cosine of that previous value, not this value, but rather of this value. Okay, cosine of time. Now it doesn't have to be time anymore. Okay, so, and the other one is sine, naturally. This will be sine. And then we'll see how we can multiply it. So sine cosine, I spread it down as necessary. It's all 0. We'll do it right. Sine, okay, I see. Okay? And this is our circle. Okay. So it only looks like an ellipse because it is resized. But you can see that it passes through the point that it's supposed to pass through. Okay, so what we did last time, and that is worth now implementing, we multiplied by 2, remember, by 2, and then the conclusion was circle radius 2. Let's do that, so we don't have to guess. So I take this, what I'm going to do is I have mu x and y, but I'm not going to compute them from scratch, but I'm going to compute them. I will take the previous values and multiply them by 2. So I take x equal to 2 times the x value, okay? And then I compute, and then naturally the same for y. Okay, now once again I spread it down as far as necessary. I could plot it once again, like this maybe. Okay. Oh, that doesn't look right. What happened here? I don't think it understood what I was trying to ask you to do. Okay, here it is. So unfortunately, I should have plotted on the same plane, so you can see. But yeah, I think you can recognize that the radius is 2. Okay, it passes through those points. Now, in addition, the last topic that came up, and that is what happens if we want to shift the circle elsewhere. You would just add a vector. Okay, so let's do that. Suppose I have a vector somewhere that I want to add. I want to use to shift my circle. I'll just put that extra vector here. Well, let me just let me modify this one. So the radius 2. What I'm going to do is say I add 2 plus 2, and here say minus 3. Minus 3. Okay, so that is, I modify x coordinate, y coordinate, and I have the same circle except it's going to be shifted. Okay, well that is my second circle. You can see that it is the same by shape and size as a radius 2, but you see that the center has become, this is now the center, and the center is 2, -3. All I had to do is to, after the fact, after all the circle is computed as a function of t, parametric curve, then I add on top of it, I did 2 things. I multiplied by 2 each of them, so that the whole thing grew by 2. It had been stretched in the horizontal direction, but also then I added that vector 2, -3, and it is the circle has been shifted. Okay, so you can still see this radius 2. This is 2 and this, so that's the radius. So that way you can do anything you want. You can also, not in a vector, so how do I turn this into an ellipse? To turn it into an ellipse, I have to actually stretch it non-uniformly in the horizontal vertical direction. So that's a different kind of operation, still to come. Okay, so that's what we do with the curve, with the circle. So we multiply by 2, get radius 2. This is what I just did, is equal to 2, say b, w, say, plus 2 cosine t sine t. So this will be shift by vector w to get this still the same. This whole thing shifts. That's what happens, and the shifting is, I hope is clear what happens. It's like a piece of paper that it was here, and then it has been shifted. So, and on that piece of paper there's this graph, and certainly the graph also shifts with that piece of paper. The stretching, slightly trickier. The stretching, because you can stretch it in different ways. So how would you describe the stretching of what we're talking about? So I multiply the circle by 2, and you see what has happened. But suppose it's a different curve. What can you imagine what's going to happen? So what if the circle was here, and I stretched everything by 2? What's going to happen? What kind of stretch are we talking about? Well, let me actually remind you that both shift and stretch is not entirely unfamiliar. You saw it in Calculus 1. Remember when you had only a function of one variable, this is x and y, but you had, say, x and y, and you have a graph, y equal f of x, and then you replace it with y equal f of x plus 1, for example. Okay, you remember what happens to the graph? If you add 1, goes up by 1. Okay, so the graph is intact and been shifted 1 by 1 unit. So y is vertical because it's dissimilar from this. You can have shifts in any direction because they are in many directions. But at the same time, that if you now look at the, so that's not really the hard part. The hard part is what happens if I multiply by 2. So if this is y equal to f of x, and then I am to consider y equal to f of x. So remember, the answer is you stretch the graph. Can you be more specific? So once again, this is a Calculus 1 question.
It's a vertical stretch.
It is a vertical stretch. Okay, so still not specific enough.
Vertical stretch by a factor of 2?
Yes, yes. But can you try to be more specific? Which way do you stretch? So do we stretch vertically? Do we stretch up or do we stretch down?
Both.
Both. Okay, so it seems like two very different things happening in different places. So that's why we have to be more specific. And you stretch it up in here and down in there. So the bottom half stretches down, the upper half stretches up. It's still where everything goes along the y-axis. So, but still, that's the complexity is as if it is a sheet of rubber, and you grab it by two pieces and shift it like this. Okay, and then so that the x-axis goes nowhere. Okay, so then similarly, what we have here is the stretching is it is a radial stretching, which keeps the origin intact. Which means that circle over there will not only be stretched in size, but also in location. So it's like a piece of rubber, and it's being stretched uniformly in all directions, so that not only things are stretching in size, which is what we did here. We stretched in size, so it was radius 1, so it became radius 2, but also everything moves to a new place. So if I'm stretching this, I'm going to have a larger circle and twice as far from the origin. Okay, so that's kind of stretching. Okay, so that takes us closer to understanding functions as transformations of our spaces. So that's what we're talking about here. Shift, number 1. Number 2, stretch. They are transformations of the plane. So what we have seen in Calculus 1, transformations of the x-axis into the y-axis. And here, a similar thing to be considered is transformations of the plane into itself. So it could be shift, stretch, it could be flip. And one thing that you never see here is rotation. So we're gonna look at that too in a short while. Okay, so circles. I guess it's no harm if we just write the ellipse, just for reference. Ellipse. So as you can see, there are the coefficients of cosine and sine are different, and that gives you the disproportional shift, disproportional stretch. So if you start with a circle, then you multiply over here by a gives you a horizontal stretch by a, and then the x-coordinate runs between if you think about it, runs between, this is x, and x runs between what are the numbers. Cosine runs between what? -1 and 1, so this runs between what?
Negative and a.
Negative and negative, yeah. So assuming that a is positive and b is positive. And similarly, b y runs between negative b and b. So that gives you a kind of rectangle that tightly contains that ellipse. So once again, you might remember what the implicit formula of the ellipse is, but we are doing parametric curve, so just as well. So like this. So negative AA, negative BB, and the ellipse is here somewhere roughly like this. Otherwise, it's very similar. This is the starting point over here, and you go counterclockwise at the same pace, and then you start to retrace yourself. You certainly can limit your domain between 0 and 2 pi, because after 2 pi, both sine and cosine try to repeat itself, so you're not producing any new points, but certainly if you want to model motion, then you go beyond and you go with t between negative infinity and infinity, so that way you can speak of motion in non-stop periodic motion. So you retrace, 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 whether it's circle or ellipse. Okay, so these are the parametric curves. Let me just do a kind of a preview very quickly of what we can do with other functions. Other functions meaning, if you remember that table that I made of the domain and range. So domain, dimension 1 and 2, range, dimension 1 and 2. This is just functions, calculus 1. This is what we've just been talking about, parametric curves, okay? And I just don't want to put too much emphasis on these, even though they're so important. The other two cells are functions of two variables. And vector fields. Okay, so this is what we have been doing. And let's take a quick look at what's left. And I want to take as an example, I want to take the law of gravity. So Newton's law of gravity. So the force, if you remember, the force between two masses, mass m1, m2, well, let's do m and m capital, is, so what do you remember this about the law of gravity?
The force between them is inversely proportional to the square of the distance between them.
Yeah, that's right. This is the what I want to especially spend time looking into. Inversely proportional to the square of the distance between their centers. Well, it's also proportional to, not inversely proportional, but proportional to each either mass. So the formula probably is easy to write. What is the gravity constant, m1, mm, and 1 over r squared. Okay, so that at least that's how you would write it in physics. So the distance being that number r, and that's the formula for the law of gravity. So first of all, before we actually look at the masters here, you can think of this as a function of 1, 2, 3 variables. 3 variables. So if you were to continue on with calculus 1, you could look at df dm, df dm capital, and df dr. the last one is the more interesting, even though, because certainly assumed in any kind of Newtonian mechanics, you assume that the masses are constant, even though if you think about a rocket, to propel itself, it throws fuel out, and which means that it gets smaller and smaller in terms of its mass. So certainly this is not something to be ignored. But our interest is the last one especially. Well, actually, at this point, we assume that these three are fixed, and we only look at R. Okay. However, it is unsatisfactory in terms of what about the direction? And certainly, well, the part that I omitted, but certainly Newton didn't, is that it is directed. It is kind of obvious, but I do believe it was not obvious to Newton or people before him what force, whatever that was, would move the Earth around or the Moon around the Sun, even if you assume that that's the case. So what moves the Earth around the Sun, and the fact that Newton discovered that every time the acceleration of the Earth is pointing at the Sun, even though the orbit is elliptic, was an indication to him that it proves that there is a force, and the force is the Sun, not some from elsewhere somebody controls the motion, but rather the Sun is pulling the Earth towards itself. Okay, so that is the part two of the law, is that the force is directed between them. Which also indicates the idea of the third law of Newton's law, that if the Sun is pulling the Earth towards itself, then the Earth is pulling the Sun towards itself. Okay, so as you can see, the formula is symmetric. So whether it is one or the other force, one or the other planet or celestial body, they were pulling at each other at this force with exactly the same force, like this. Okay, so we assume then still that these are fixed, and look at what happens to R, and we want to translate this into a vector equation, because so that we wouldn't have to worry about directed between them and describe it verbally rather than let's just do it algebraically. But before we do that, let's do before we do that, let's just step number one would be to just look at R, the meaning of R. It is, in fact, the distance. It is the distance, and we know the formula for the distance. Say you mentioned 3 or 2, doesn't make any difference. So in our 3, R is the distance. So suppose let's put the Sun in the center of our Cartesian system. So it will be x squared plus y squared plus z squared. Right? The distance from the origin to the Earth. That way, we have f becomes a function of 3 variables. These are less important, and we have 1 over squared, right? So it will be x squared plus y squared plus z squared. 3 variables. And we could do whatever we want with them or with this function. We can study it. We can plot it. We'll probably not today, but certainly there would be no trouble to do what we did a couple of weeks ago, plotting the graph of a function of 3 variables. Well, 2 variables. 3 variables can work out. But if we just drop the z, we can plot it. You probably can guess what the graph of this function looks like. If we forget about z, what does it look like? No, it's a cone. Think about one variable at a time. If x goes to infinity, what happens to the whole thing? So the two bodies are separate from each other. What's happening?
The force is going to, it goes to 0.
It goes to 0. The force is negative, which will make sense, right? On the other hand, if you were then getting closer to each other, then what happens to the force?
Goes up.
Well, if x is going towards 0 and y is going towards 0, there's no z. What's happening to the f?
What? Increases?
Increases how far? To infinity. So that's another limit. The one limit at infinity, the other limit at 0. Both of them are, in other words, we have two asymptotes. You can probably, we will confirm that, but that's what it will roughly look like this. So it's getting flatter and flatter away from the 0, and here it goes up to infinity. Certainly, that never happens because there is an extra, like amendment to Newton's law. What happens to the gravity as one of the objects starts to penetrate through the other, and there is actually what's happening is, well, what happens if you drill through the earth, all the way through the earth, and drop something in there. The gravity will be declining as the object is dropping down. Okay, so if you are here, if your object is here, this part of the earth, Earth gravity disappears. It does not, according to Newton, he discovered that too, that it's like the radius is shrinking. Okay, so which means that as you're going closer and closer to the center of the Earth, the force becomes 0 at the end. So if you have weightless, you have weightless because if you're dropping freely, but suppose you try to walk down, then at the very center you will have weightless. So that part then does not really reappear. There's more complex statement of the problem. And so let me just do one more thing, and that is let's state it in the form of a vector valued function. So f of x, vector of 3 variables, GMM, and what is the denominator? So this is the vector of location. Well, actually, I don't have to vector of location. I could say just location. Then I could just put it in the form of d0x. So we are at location x. All we have to square. All we have to compute is just the distance to the 0. If you prefer vector notation, then it's the same, except you're going to have the magnitude of x, like this. Okay, so that's all for today.